Hello everyone, welcome to another interesting lecture of digital signal processing. In today's class, we are going to talk about FIR design using Fourier series method. So your FIRs are finite impulse response filters. We have seen about the types and properties of FIR filters in our previous lectures. And today we are going to see how we can design an FIR filter to do certain operations like frequency selection. Mostly frequency selective or frequency transformation operations can be done using FIR filter. For example, we can have a low pass filter which will allow or which will pass your low frequency, and you can have a high pass filter which will pass your high frequency and block the remaining frequencies. So the FIR design using Fourier series method is very simple. So it just states that your H of n, so which is your FIR filter representation. So H of n can be obtained using your Fourier series formula. So the Fourier series formula for H of n is given to be 1 by 2 pi integral of minus pi to pi H of omega e to the power of j omega n d omega. For those who are familiar with Fourier series, you know that formula is your inverse Fourier, and the magnitude response or the h of omega can be obtained by taking sigma n equal to minus infinity to plus infinity h of n e to the power of minus j omega n. So these are analysis and synthesis equations, so or forward and backward equations. And now for FIR designs, it says that if I am putting my e to the power of j omega equal to z, so the conversion is happening from Fourier to Z transform. So the original equation we have taken is a Fourier series equation, and then we have converted that into a Z transform equation, and that gives your FIR representation. So this is the original FIR. So which means like every FIR that you see. So without if I don't say FIR as a Hilbert transform or FIR as optimum equiripple filters, if I just say FIR, it is assumed that by default the FIRs come from Fourier series. So the FIR representation h of z is equal to h of n z to the power of minus n, and z is always e to the power of j omega. So by default, when I say a linear phase FIR filter, I'm talking about a Fourier series design. Okay, so the default design for your FIR is your Fourier series, and as technology evolved and we needed updates to the original FIR, so we had come up with more advanced FIR designs such as Hilbert transform, frequency sampling, optimum equiripple design. So these are some of the advanced designs. So we'll be seeing we'll be seeing Fourier series as one of the design, then window design, that is the second one, and for frequency sampling. So we'll be seeing three designs in our lecture series, and then the other designs maybe I'll put it as I'll later on maybe I'll upload those classes. So now the FIR representation for m equal to 5, right? So it is given to be this. So now what I'm trying to show you is the symmetry across the origin. So now when I am talking about Fourier series method, your Fourier series indicate that your samples are extending from minus infinity to plus infinity. So which means my series, my FIR filter is also from minus infinity to plus infinity, and that is not possible because that doesn't that is not going to be finite. So in order to induce or in order to make this finite, the first change I'm doing, that is I'm converting from minus infinity to plus infinity. I'm taking that to be now minus m minus 1 by 2 to plus m minus 1 by 2. So I'm putting that I'm inducing finiteness into my Fourier series form, and I get the form to be this. Good. The equation that I've shown here is h of z, and now I've just generalized. So I've taken an example for m equal to 5 and expanded it, and then I'm showing you that how I can generalize this expression for h of n. So I'm next, after I induce my finite, I wanted to introduce my what? Symmetry. So your linear, what are the properties of your FIR filter? So your FIR filter must be finite, it must be linear phase, it must be symmetric, it must be an LTI. So these are the very basic fundamental property that has to be present in all your FAR filters. So we started with the Fourier series equation, and now we are moving towards adapting that equation to a complete full-fledged FAR filter. So when I want to make that Fourier series formula into a full-fledged FAR filter, I have to make sure that it satisfies all the properties of the FAR filter. And the first property was finiteness, and that was I made sure of that from m minus 1 by 2 to plus m minus 1 by 2 by restricting the upper limit and the lower limit. The second one was the symmetry, and I have induced the symmetry with this formula, h of n into z to the power of minus n plus z to the power of n. The third one is the causality, another important property. So the above expression, whatever I have written, is symmetric and finite, but it is non-causal. So it is not causal because it doesn't satisfy the condition. My h of n is not equal to 0 at n less than 0. So for causality, your h of n must be 0 for n less than 0, because this is the non-causal condition I have here, because the positive powers of z means that my sample index is occupying the negative position. So that is what it means, right? So I'm telling that from minus m minus 1 by 2 to plus m minus 1 by 2, which means I have samples, I have values, I have filter coefficients on the negative side of the origin. So these negative values must not be there if I want my filter to be a causal filter, right? So to remove this non-causality, or to make your filter causal, what I am doing is I am taking that negative coefficients and I am shifting it to the positive side, and I am doing that shift by this multiplicative z to the power of minus m minus 1 by 2. So when I multiply with this z minus m minus 1 by 2, all the negative coefficients, right, the negative index values are now shifted to the positive side. So what will happen is, before, if I had z1 which was occupying n equal to minus 1, that would be pushed, if m is equal to 5, it would have been pushed to what, z of minus 3, so it will be pushed to some place like 1, right? It will be pushed to n equal to 1. So that is what will happen when I multiply with z to the power of minus m minus 1 by 2. So I am showing this example for the same m equal to 5. I am doing the expansion after I multiply with z to the power of minus 2, and then let us see what do I get. So when I do this transformation, then I'm going to see only negative powers for z. So that means all my sampling positions are on the right side of the origin, or on the positive axis. So z minus 2 indicates my sampling position 2, z minus 1 indicates my sampling position to be 1, z minus 3 indicates my sampling position to be 3. Alright, so these are how my sampling positions are being, it gets shifted to the right side of the origin, thereby making my FAR filter causal. See what all we have done. We started with the Fourier series equation. That was because we are talking about FAR design using Fourier series, and then the first thing I did was make it finite. The second thing I did was what, I induced symmetry. I made sure it is symmetry by taking Zn plus z to the power of minus n. And the third thing is I removed the non-causality, or I made it causal. I converted it from non-causal to causal form by multiplication with z to the power of minus m minus 1 by 2. And what is causality? It's just the same thing with the past, present and future. So your system depends on only the past and present and not on the future events. So the same thing, but I'm in mathematical form for FIR, I'm just calling that to be Hn not equal to 0 for n less than 0. So that is a non-causal expression, and Hn equal to 0 for n less than 0. That is your causal representation. Good. So when I multiply, so I'm just making it clear for you how to convert. So it's very important, because even in the numericals that we'll be seeing, it is vital that you convert a non-causal representation into a causal representation by multiplication with z to the power of minus m minus 1 divided by 2. And that is not going to have much effect. So we are talking about what is the effect that's going to happen, that's going to have on your FAR filter. If you look back at FAR derivation, you will be seeing that z to the power of minus m minus 1 by 2 is Nothing but your phase. So your linear phase is proportional to m minus 1 by 2 into frequency. So you're multiplying by z to the power of minus m minus 1 by 2 is not going to alter your frequency of the signal. It's not going to affect your signals, but because your signal is being multiplied with this FIR filter, right? When you filter a signal, you're applying an FIR to an input signal, so it's not going to affect your signal, but it's just going to alter the phase of the signal a bit, which is acceptable by all means, because that's not going to have much effect on the quality of sound, because if it's a sound filter, it's not going to have much effect on the quality of sound by doing that. Okay, so let's start this numerical now. So we have seen the design, so FIR design using Fourier series. So now I'm going to apply that to a numerical here. So the question is to find an ideal LPF. So we have to do an ideal LPF design, and then we have to plot the magnitude response for a low pass filter, right? When I say an ideal LPF, it is nothing but your low pass filter. Now the h of omega is given to be 1 from minus pi by 2 to plus pi by 2, and 0 for pi by 2 to pi. Alright, so now let us see this. So let us see my magnitude response. So my m is equal to 11. So question says m equal to 11, it means it's symmetric and odd. So I am writing this h of minus 1 by 2 plus, so the magnitude response formula is this, because first I have to design my LPF, that is find my h of z, and then I have to find the magnitude response. So in order to do the magnitude response, I need to know the formula of magnitude response. So I'm writing the formula for my magnitude response. Alright, so and what is my h of n? So h of n is my FIR filter, and that's gonna be my FIR design equation, 1 by 2 pi minus pi to pi h of omega e to the power of j omega and d omega. So why the 2 pi? That is 1 by t, that is, that is the total duration, minus pi to pi. So that is equivalent to 2 pi. Alright, good. So I don't want to go into the Fourier series right now. So these are the two equations we will be needing for solving such problems. So the solution 1 will be using that equation, integral equation, and the solution 2 will be using the magnitude response equation. Alright, so let us do the integration first. So I know I can tell from the question, I can see from this graph that from minus pi to minus pi by 2, the response is 0. And from minus pi by 2 to plus pi by 2, the response is 1. And from plus pi by 2 to pi, my response is 0. So if I am doing this rightly, so the integral is going to be looking like this, plus minus pi by 2 to plus pi by 2, 1 e to the power of j omega and d omega, because that is the only integral that's going to be there, because other things will become 0. So the first and the last one becomes 0, and it just cancels out. So now I am just looking at the integral where from minus pi by 2 to plus pi by 2, and if I am doing this right, I am going to get this to be sine pi by 2n divided by pi n. So I know this because I get just I'm just because of I am seen many times this thing, so I'm able to tell it. But you may have to do these steps to reach it. So we are going to use the Euler formula, because we are seeing that e to the power of j theta. It should be minus actually. I don't know why I've written plus there, because it's upper limit minus lower limit. So I'll be correcting it, I think, yeah, because when I write the formula, I remember I corrected it. Yes. J theta minus, yes, I'm doing it now, yes. So e to the power of j theta minus e to the power of minus j theta by 2j, and that is equal to your sine theta. So your h of n, so now your FIR filter, your low pass filter, which is designed to the h of omega given in the question, is h of n is equal to sine pi by 2 n divided by pi n. And now taking symmetry, so I'm this, since our question is from minus pi to plus pi, so for m equal to 11, I'm going to be having symmetry from minus 5 to plus 5. Alright, so my symmetric LPF is going to be from minus pi to plus pi. So which means if I do from 0 to 5, yeah, that should take care of the other thing. Other side will be exactly the same as this side because it's a symmetry. So both halves are equal. First half of my filter is equal to the second half of my filter. Good. So let me just talk about symmetry. So I'll just show you what are the symmetries I can have. I can either have all on the positive side, then my center of symmetry is going to be 6, or I can have half on the negative side and half on the positive side. And in this case, the center of symmetry will be 0. And that is what we'll be using because it's very specifically given in the question that your question is from minus pi to pi, because that means it is the symmetry is about the origin, about the 0 axis or about the y-axis. So that is what our question says. So that is the second symmetry. I'll be writing that also. So it should be like 0, minus 1, minus 2, minus 3, minus 4, minus 5. And on the right side, I'll be having 1, 2, 3, 4, 5. And this is what we are looking at. So the example 2 is what will be used in our numerical. But the symmetry tells me what are the coefficients that are going to be equal. So I can tell my h of minus 1 equal to h of 1, h of minus 2 equal to h of 2, h of minus 3 equal to h of 3, h of minus 4 equal to h of 4. So this will, yeah, it is obvious. You may say, you can just write it, but if I thought I'll show it once, maybe in the first numerical, since this is the first numerical on FIR, I thought I'll show this to you. And probably from the next numerical, we'll be doing at least 4 numericals on FIR. So, and the next numerical, I may not be writing all these detailed steps. Okay. So, because this is a low pass filter question, the next question we are looking at is probably a high pass filter. Then I'll be doing one on band pass, and then I'll be doing one on band reject or band stop filter. So those are the 4 numericals I'll be solving in class, but I do expect you to practice more, because the more you practice on these questions, the more command you get on, and the less chances of making mistakes and wrong calculations in your exams. All right, so this is the symmetry we'll be using, and we are going to stick with the negative symmetry. Right, negative means it's the symmetry across the origin or the y-axis. That is mainly because our question says the minus pi to plus pi. So just it's because of that is the reason we are not going for the positive symmetry. And now I want to find the values for h of n from n equal to 0 to pi. So what I have written here is this is a small program from Scilab. So we are having a Scilab for DSP. So I suggest you use for your exam, you need to use your scientific calculator. So but here I am just doing my Scilab program. I've done I'm just doing the sine pi by 2 and by pi n in Scilab, and I'm writing the answers here for you to see. Okay, so now what I can tell is my first one. So all the other values are acceptable for me, but my first value, that is h of 0, is it's NaN. So what is NaN? NaN means not a number. So Scilab gives this not a number whenever it gets a 0 by 0. Because when n is equal to 0, I get sine pi by 2n divided by pi, and I get 0 by 0, and that is not a number. That is the output is not defined, or it's not a number. Now what we do in such cases, we cannot take this NaN, but we will instead use the limits to compute h of n at n equal to 0. So the limit formula that I am relying on is limit theta tends to 0 sine n theta, or sine theta by theta is equal to 1. So I'm going to use that here. So I'm going to write it as limit n tends to 0. So my theta equivalent is n sine pi by 2 n divided by pi by 2, because the theta has to be same on both. So when I induce that 1 by 2 in the denominator, I'm going to get an 1 by 2 outside. So that is going to give me 1 by 2. So I can write my h of 0, or which was before NaN, or not a number. By applying limits, I can tell that my h of 0 is equal to 1 by 2. So now I have all the values for my h of n. Good. So now I can go on to write the h of z, because h of z is from obtained from the h of n coefficients. So I can write my h of z, and I will definitely, when I write my h of z, it is from -5 to +5. So I'm definitely going to end up with a non-causal representation. Because why? Because -5 to -1. So these positions on the left side makes it non-causal. So I want to make it causal. So what I'm going to do is I'm going to multiply it with z to the power of minus m minus 1 by 2. When I do that, I'm shifting this entire signal from -5 to +5 to 0 to 10. Yes. So that is exactly what will happen. So I'm just shifting the signal by multiplying it with the z to the power of minus m minus 1 by 2, and then I get coefficients from h0 to h10, and that is your FAR representation. Good. So that is the solution 1 to this question, and after that we need to find the magnitude response. So let's get started on doing that. So I'm writing these formulas for you, because what is the h of z formula in FAR design? That is h of 0 plus h of n z to the power of n plus z to the power of minus n. So I'm doing that same for 0 to 5. So I get it in this form. Then after I get that, then I need to convert it into my what, non-causal to causal, because what I write here, this is a, so I can show that, I can clearly say that I have positive powers, and these positive powers makes it a non-causal. So in order to induce causality, what do? I multiply it with z to the power of minus m minus 1 by 2. So the steps are the same. So we are going to see different design techniques, and we are going to do different numericals for each design. But in every design, you will see that this non-causal to causal conversion is the same, and it exists in every FIR design numericals. So irrespective, I can say that irrespective of the designs that you are adopting for your FIR filters, this symmetry across the origin has to be removed, right? That is what it means. So I'm turning from non-causal to causal by shifting it from -5 to +5 to 0 to 10. The index, I'm talking about the index, which was -5 to +5. That is going to be shifted to the right, and it's going to now look like 0 to 10. See, now I have written this after multiplication with z to the power of -5. Now I can see that the coefficients, see, it's from 1 to 0 to 10 I'm having, and this is a causal representation. I can directly tell, I'm going to write in steps, but I can now tell that my z minus 4 is my h of 4, and z minus 6 is my h of 6. So my h of 4 and my h of 6 is equal to h of 1. I can just write the values and multiply it, but in many MCQs they ask this in terms of this h of 1 to h of 10. So that is why I'm writing this, because if I just plug in the values, because I know what is h of 1 to h of 5, if I just plug in the values and multiply it, then I get the FAR representation. It's as simple as that. You can do that. From next numerical I'll be doing that, but for now I wanted to show you how, what is, suppose the question is you have h0 to h5, which is in the non-causal form. In the causal form, h1 is equal to what? So in that case, you have to write h1 is equal to h4 and h6, and your h2 is equal to h of 3 and h of 7. So this conversion has been asked in, I've seen this question asked in many exams, many places. So you have to be able to tell, because they say convert this causal representation, right, non-causal to causal, and what is the coefficient reordering. So when you reorder the coefficients, you know that what was h2 is now h3 and h7, and what was h3 in the previous case, the blue represents the non-causal, the green represents the causal, that is now h2 and h8. So the same way I can write, or I can do for h4 and h5, that will be equal to h1 and h9, and h5 will be equal to h0 and h10. And then I can put these values, and then I write my FR. So my solution 1 is almost ready. Solution 1 is just, I can do it at that white equation, the first equation I can, and after that itself I can write one step. where I put all the values. I put h0 to h5 values in that equation, and then that is your representation. Okay, but I've shown how the coefficient reordering happens, so that it helps you in your this MCQ exam. So that is why I've shown you this. Good. So which was h0 in non-causal is now h5 in causal. That is what, 0.5, right? 1 by 2, it was 0.5. Good. Now I can write the FIR final representation for low pass filter. So the question given low pass filter, the FIR form is given h of z, h of 1, h of 2, h of 3, etc. So now it's going to look in this manner, and I know what are these values. Okay, so I can write it. Okay, good. So I'll plug in these values and then I get my solution 1. So after I have my solution 1, I'll go to my solution 2. That will be the magnitude response. So I'll be finding the magnitude response. Okay. So let me write this. So let's, in the question it says the frequency response, and mostly when they say frequency response, it is, they mean magnitude response. That is a h of omega. So we are not, and you can do both. You can do the phase response and the magnitude response, but normally the questions are asking you for this magnitude response. So m equal to 11. This is the magnitude response formula I have because it is an odd symmetry. So h of m minus 1 by 2 plus sigma n equal to 0 to m minus 3 by 2 h of n 2 cos omega m minus 1 by 2 minus n. Alright, so that is your formula now, and I'm just gonna put value of m equal to 11 and I end up getting this. So let me just expand the summation n equal to 0 to 4. I am gonna get h of 0 2 cos phi minus, yeah, so h of 0 cos phi omega, h of 1 cos 4 omega. Excellent. So this is the form that I'm having. And now what I need to do is I need to plot my magnitude response, which I can do by plugging in the values of omega. So I'm going to put the value of omega to be from 0 to 180, right? So I'm going to plug in the value of omega to be from 0 to 180, and then I am going to plot the results for these values. So I'm not, you have to do this on on a graph sheet in an exam. Given you a scientific calculator, you can compute all these values, make the table and plot it. However, in this lecture, for our lecture, instead of doing that, I'm gonna make use of the Scilab, which is also a scientific calculator. It's a programming calculator. So I'm going to use Scilab, and I'm just gonna run this equation for different values of omega, and then I'm going to just plot these output. All right, so let us do that. So what will I'm going to do that exactly. So let me write, um, if I want this in dB, what I do is I just take the 20 log 10 dB, logarithm to the base 10 of h of omega, and that should give you the dB graph. Because in your exam, when they sometimes they ask for dB, so in that case you need to use the semi-log graph for this. And if they ask you to just do the, just if it is a magnitude response, you can do it for just h of omega. All right, so let us see. So you have to plug values of omega to be from 0 to 180, and we are going to do that. Then we will see how it looks. Okay, clear. So this is the solution too. So this is pretty much how you do these questions. Most of the questions are something like, along the same line. So we'll see this. So this is the Scilab program I have written, and you can see here I have written that equation. So the equation given above is shown in h of count, zero point 0.5 plus 2 exact thing I have written there, and you get the output. Okay, thank you.